Okay, here we are for some more problems from worksheet 1. Let's take a look at problem 3. It says an astronaut floating at rest in space whose mass is 80 kilograms carries an empty oxygen tank with a mass of 10 kilograms. He throws the tank away from himself with a speed of 2 meters per second. With what velocity does the astronaut start to move off into space? Okay, so take a look at this. You say we can draw our before and after pictures. Again, I always like to draw a picture of the system before the interaction, after the interaction. So here we go. Astronaut, oxygen tank. Right? And that's our before picture. They're at rest, right? So beforehand, we know the speed is 0. We know that the mass of the astronaut is 80 kilograms. We know the mass of the oxygen tank is 10 kilograms. Okay. Afterwards, they tell us that that tank, he goes ahead and checks that oxygen tank, and it goes flying off at 2 meters per second. Let's go ahead and decide right now. Let's call to the right positive as a positive 2. Okay, what's going to happen to that astronaut, right? And you say, well, that astronaut, you say, okay, and I anticipate that that astronaut okay, I anticipate that astronaut's going to drift back to the left. Lost the astronaut final. Yeah. Okay. You say, yeah, because the total momentum at the start is 0. If the tank gains momentum to the right, he's got to gain momentum to the left, because in our combined system, there's no outside force acting on it, so momentum's got to be conserved. Let's take a look at this. We're going to go ahead and analyze to find this. You say, hey, what do we want to make our system? You say, do we want to make the system be just the astronaut, just the tank, or the tank and the astronaut together? We're trying to find the velocity of the astronaut, so we really want the astronaut to be involved. But they gave us some information here about the tanks. I think I'm going to need to do a combined system. So my system is going to be the astronaut and that oxygen tank. Let's go ahead then and do the big formula for this unit, which you say is that impulse is equal to the change in the momentum. Right? That's our big formula for the unit. Astronaut and taking them together, astronaut and tank, are there any outside forces acting on them, floating out there in space? And we say, nope, no outside forces. And so this left side of this equation, you say, bang, right? No outside forces. So you're like, okay, well then that means my change in momentum is 0. We could go ahead and break that out into a change in momentum for the astronaut and a change in momentum for that oxygen tank. Right? If I did that, you say, let's go ahead and substitute in MV for each of them. So change in momentum, and that's going to be like, actually, you know what? Let's split up the deltas first. Let's expand the deltas. This would be momentum of the astronaut at the end minus momentum of the astronaut at the start. Yeah. Plus momentum of the tank at the end minus momentum of the tank at the start. There's always final minus initial. Are any of these 0? And you say, yeah, sure, they were both sitting still at the start. And so the initials are going to drop out. Okay. So when I look at this now on the right, I just have momentum of the astronaut plus momentum of the tank, right, at the end. Together they have to add to 0. You're like, that means one of them, they got to be equal but opposite to add to 0, or both be 0. But this isn't 0. So that's got to go to the left if that's going to the right. So they have a negative term and a positive term to balance out. Let's go ahead and substitute in P as MV for each of those. Momentum of the astronaut at the end. This would be the mass of the astronaut, the velocity of the astronaut at the end, plus momentum of the tank at the end, mass of the tank, velocity of the tank at the end. Right? We are trying to find this one, the velocity of the astronaut at the end. You want mass of the astronaut? 80 kilograms. Mass of the tank? 10 kilograms. Velocity of the tank at the end? 2 meters per second. We know everything. We can solve for that. That's just going to look like this. 0 is mass of the astronaut, 80. Times velocity of the astronaut at the end. plus 10 kilograms with a velocity of 2 meters per second. Rearranging that, we are going to get that velocity of the astronaut at the end is going to come to be negative 0.25, negative a fourth meter per second. You say that checks out, that makes sense. This astronaut, the total momentum is 0 at the start, so the total momentum at the end, because there's no outside impulse, the total momentum at the end's got to be 0. The tank has only 1/8 of the mass of the astronaut. So the astronaut's got 8 times the mass. He needs to have 1/8 the velocity. Then to balance out, 1/8 of 2, it's 0.25. That makes sense. Makes sense. It's negative to make the total add to 0. So that's it. That's problem 3. All done. Okay. Let's move on to problem 4. Okay, I'm going to do both problems on this one. I don't know, maybe I'll have time to sneak in another one. We'll see. Okay, problem 4 says a tennis player returns a 30 meter per second serve straight back at 25 meters per second after making contact with the ball for a half a second. If the ball has a mass of a fifth of a kilogram, 0.2 kilograms, what's the change in momentum of the ball? So here we go. What does that picture look like? Right? And again, you may draw this picture a little differently than I'm going to draw it. I'm going to say, I'm going to draw it just for the heck of it. Let's say, hey, here's that ball. And I'm going to go ahead and draw the initial velocity being to the left. Left or right, you may draw it a little differently. I'm fine. Either way is going to be fine. We'll just say that the velocity of the ball at the start is going to be what? Let's make that count. It's going to be negative 30 meters per second. I'm going to call, right away, I'm going to call it the right positive. Okay, I'm going to choose that. Okay, now it says she hits the ball back, right? The ball gets hit back, so afterward the ball is going the opposite direction, right? At 25 meters per second. Okay, I might give that a name, velocity of the ball at the end. VB final. So it's a positive, is negative velocity. Okay, what else do we know? They told us the ball has a mass of 0.2 kilograms. Kilogram, which seems a little heavy for a tennis ball, frankly. And then lastly, they tell us that the time during which that racket is in contact pushing the ball, that duration of the push is a half a second. And what they're asking us to find is, let's be real careful here, they want us to find the change in the momentum of the ball. So what they're asking us to find is what's delta P for the ball, okay? That is what they want us to find. All right, so taking a look at this, when I go from here to here, that ball is going to interact with something outside itself, and that's that racket, the tennis racket shoving on it. If I go to the big formula for this unit, F delta T is delta P, yes, that is the big formula. You say, hey, I need to choose my system. Well, right away you say, I don't know anything about that racket, right? Except the duration of the time the ball is in contact with it. And so you're like, so I really can't make the system be the ball and the racket, okay? I just don't know enough information. I'm gonna have to make the system be just the ball. I think that's pretty clear, all right? So, is there an outside force acting on the ball between here and here? You say, yeah, the racket's shoving on it. So this side is not going to drop out to be 0 this time. And you're like, okay, hey, I'm trying to find the change in momentum of the ball. You know what? This is actually what I'm trying to find. I'm trying to find that delta P ball. I'm like, oh, okay, well, do I know the force acting on it? No. I know the time it acted, but I don't know the force. Like, wait a minute. I don't know the force. I'm trying to find this. I only know 1 out of 3 variables. I'm not going to be able to solve this using this side of the equation. I'm not going to be able to find that F delta T. So what instead I'm going to do is just work with this right side. Delta PB, that's going to be my momentum of the ball at the end minus my momentum of the ball at the start. Can I calculate these? And you're like, oh, I can. I've got the information. I can find the final momentum of the ball. I can find the starting momentum of the ball. I can calculate the delta V just calculating this side. I'm not going to need this side at all. Okay, you see that? So I'm not going to use this side. I'm going to use this side of the equation because this side is just equal to delta PB. So say PB final. That's going to be using momentum equation, right? Mass of the ball, velocity of the ball final minus PB initial. Mass of the ball, velocity of the ball initial. You say, hey, do I know mass of the ball? Yes, I do. I know that mass of the ball, they told me, is 0.2 kilograms, right? This is going to be 0.2. The velocity of the ball at the end is a positive 25 meters per second. Minus mass of the ball, 0.2. Velocity of the ball at the start, that was a negative 30. It's going to the left. Okay. And so I can just do the math here. Hey, you know what this is? 0.2 is a fifth. A fifth times 25, that's 5. And then a fifth times 30, that would be 6, right? You say, but negative and negative makes that positive. You say my change is a positive 11, and then my units for momentum are kilogram meters per second. Okay, so that is this side, that's the delta PB. Does it make sense to you that the change in momentum is positive? That means the change in momentum is to the right. Remember, delta P's got a direction to it. I had a momentum left, and then I end up with one to the right. Final minus my change, say the initial plus the change gives me the final. That change better be to the right. Okay, so good enough. 11 kilogram meters per second. Okay. Now, quick side note. All right. You're like, hey, wait. Why did they tell me the time here of that impact? I didn't end up needing that to solve this problem. Right? Didn't need the time during which that racket was shoving on it. Here's a question that someone might ask us. Could they ask us, given this information, can you find the force, the average force that the racket shoved on the ball with? So I know the force of the racket is actually going to be changing during that impact, right? As the ball hits the racket strings and the strings stretch and then decompress, right, and then come back. You say restore. You see that force is going to be changing during that. But if we imagine there was, on the average, one constant average force during that impact, could you find that average force? You say, yeah, we could. Now that I know the right side here, delta P is 11, I know the time is a half. I can solve what that average force was during it. If I did that, plug in my values here, this would be a half of a second times that average force. We put a little bar over a variable. We mean the average value, by the way. That's the notation. You'd say, hey, what would that be? Average force times a half is 11. Divide by a half, it's like multiplied by 2. That average force was 22 newtons. Was that average force? So we could solve for that. We weren't asked to solve for that in this problem. Okay? We didn't need to do that. But good to see that we can figure that out from the information given. Okay, so that was problem 4. Okay, the tennis problem. Okay, let's hear, and there was problem 3. I did the astronaut too. That's two problems for this video. I'm going to stop this video here, and we'll do problem 5 on the next one.